In Proposition 35, we're going to prove an interesting truth about the equality of areas of two parallelograms under a special condition. Parallelograms, which are on the same base and in the same parallels, are equal to one another. Let's check out the setup. Let ABCD and EBCF be parallelograms on the same base BC and in the same parallels AF and BC. So we're going to have to draw this up. So we have that common base, which is going to be BC. That's going to be BC. We're going to have our first parallelogram over here. And then what we're going to do is draw this over, like so. And then we're going to have another parallelogram which is built on the same base. And the claim is that the areas swept out by these two parallelograms are equal. And in terms of labeling, we have our common base BC here. This is going to be A, and this is D, so that what he's talking about here, the parallelogram ABCD, that's this one over here. And over here, we're going to have the parallelogram EBCF, so this will have to be E, and this will be F. And later on, he's going to call this intersection point G, so we'll just place that in here. And the claim is that I say that ABCD, this parallelogram over here, is equal to the parallelogram EBCF. And equal, in context here, he means that the same area is swept out by the two parallelograms. And we proceed to prove this. For since ABCD is a parallelogram, AD is equal to BC by Proposition 34. So opposite sides in the parallelogram are going to be equal. For the same reason also, EF is equal to BC. Let's take note of that. So EF and BC are going to be equal. Again, opposite sides of a parallelogram must be equal. So AD is equal to BC, which in turn is equal to EF, as he says, so that AD is also equal to EF by common notion 1. And we have DE in common. So we'll take note of DE. And what he's going to notice here is that since we have AD and EF being equal, what's going to follow from this is that AE is going to have to be equal to DF by common notion 2. Equals added to equals will make the wholes equal. So we have, therefore, the whole AE is equal to the whole DF. So this DF here is equal to AE. And we also note that AB is equal to DC, again using Proposition 34. Opposite sides of a parallelogram are equal. Therefore, the two sides EA over here, actually I'll highlight that just to make the triangles clear. So we have EA and AB, he says, are equal to the two sides FD, which is over here, FD and DC, respectively, which is true. He also notes that the angle FDC, which is right there, is equal to the angle EAB, which is over here, which follows from Proposition 29, because we have two parallel lines, AB and DC, being cut across by AF, so that these two angles must be equal. And notice in these two triangles that we almost had illustrated, we have this triangle right here, ABE. Notice we have AE that was in common with DF, and AB is in common with DC. And we have these two angles in between the two respectively equal sides also being equal. So therefore, we're going to use side angle side, Proposition 4, to conclude that these two triangles must be equal. And we make our usual inferences from that. And we conclude that the base EB is equal to the base FC. So I'll remove that. So what do we have at this point? We have the equality of EB with FC, which we knew anyway from this being a parallelogram, but we may infer it from proposition 4, side equals side. And as he says, the triangle EAB will be equal to the triangle FDC. Now here's an interesting step. We're going to take those two equal triangles that I highlighted before, EAB and FDC, and we're going to subtract away DGE from both of those. So from this triangle and from this triangle, we're going to subtract away this triangle right here. And if we subtract away this triangle from equal things, what results will be equal? Therefore, the trapezium ADGB right here is equal to the trapezium EFCG, or in the order that he writes it, ABGD is equal to the trapezium EGCF. Those two trapezia are equal. Now he says, let the triangle GBC be added to each. So we're going to add in this triangle, GBC, to each of the two equal trapezia. And if we add in this triangle to the two equal trapezia, then notice that we just get the two original parallelograms, namely ABCD and EBCF. And an equal added to equals will generate equals. Therefore, the parallelogram ABCD will be equal to EBCF.